is not like that at all. ENM is the most pure and beautiful physics theory that we have, in my opinion. And for that reason, I just think it's just the way in which we have a physical description of electromagnetism is sort of the foundation of how we do physics. And so I think there's a few different aspects of it. I just want to just kind of get the ball rolling with. I mean, it's sort of the model of the scientific method. I mean, so, you know, part of the scientific method is empirical, right? I mean, we have phenomena. And we do measurements. And, you know, back in the 18th and 19th century or before, I mean, people were observing different phenomena that associate, you know, shocking frogs' legs, sticking lodestones into coils and seeing and noticing stuff happening. And, you know, and part of the physics is to not just have a description, we see this, it does this, but to create models and they're generally mathematical models, which allow us to get some kind of, you know, unified description. So not to think about each phenomena on its own, each particular thing, but a whole class of phenomena that we can unify and say this is the model that describes those things. And that unified description should allow us to make predictions of things that we haven't observed in the past, right? So there's a feedback here whereby if it's a good model, if it's a good theory, you know, this is one of the things that annoys me to no end, and you'll hear all my little pet peeves, because that's just how I am, I like to talk about that. You know, people use the word theory in this way as if it's just imagining, you know, that's our imagination. Well, that's just a theory, right? But the term theory is the fact is that it should be predictive. If it's a good theory, then it's not just, well, I just think this is true because I like it. It's because it allows us to make a prediction that we can quantify in the world later. That's what we want from our scientific models, right? And then we see those new phenomena, and it helps us refine our models, and there's the feedback. But there's another aspect of this which I think is particularly beautiful, and is particularly, I think, exemplative of electricity and magnetism, is the notion of self-consistency in the model itself. The model should be consistent, whatever the physical model we produce, the mathematics that we use to make these predictions, to make unified description, should be consistent within themselves. And if there are inconsistencies, then there's something wrong. And this, of course, was, you know, the amazing example in electricity and magnetism, which, you know, was Maxwell, Maxwell in, you know, whatever that was, in the 1860s or 50s, God, I should know, but anyway, around then, around the time of the US Civil War, saw an inconsistency, that the equations that had been developed that described the phenomena that we saw were inconsistent with charge conservation. Which was an observed principle, that charge is conserved. And the fact that the equations were inconsistent would say that charge wasn't conserved led Maxwell to add the famous displacement current. By the way, I didn't mention this, but I should have. There are prerequisites for this. I assume everyone knows that I assume everyone has taken the equivalent of undergraduate E&M, okay? If you haven't, it's gonna be more challenging. But I'm assuming, and this course assumes that it's a prerequisite. It's not a requirement, I'm not gonna waive it, but I just let you know that we're not starting from the beginning. We're assuming everyone has taken an equivalent of Griffith's E&M at the undergraduate level. Right, so, you know, the inconsistency here led a refining of the model to ensure that it was consistent with those physics principles. And that, correcting that, led to a new prediction that wasn't seen, but was predicted purely from the theory. And that was the prediction that light is an electromagnetic wave. Oh my God, how beautiful is that? Which of course was then observed in famous experiments by Helmholtz, right? And you might ask, well, why didn't they see it first? Why did it have to go through this, you know, back door of theory? Why didn't we see it? And, you know, it's not always the case that natural phenomena happen in the laboratory and in all conditions. We might not have known the conditions that we needed to set up in order to observe that phenomenon. And that was laid out in you know, why the displacement current, and we'll come back to that, why was the displacement current not part of Ampere's law at the beginning? Why did it not occur? Yeah.
So did the displacement current start out just a fudge factor and people investigated it and said, hey, this actually is.
That's right. I think the term fudge factor is a little, you know, we wouldn't necessarily that cheap way of saying it's really a brilliance. It wasn't like, there are fudge factors that we do in physics, you know. The Lorentz oscillator model of the atom was a fudge factor, you know. They put in what were called oscillator strengths to explain those spectral line shapes. Those are fudge factors. This is more a theoretical breakthrough. Yeah?
In definition of a theory, is it necessary for it to also be falsifiable?
I would say that's a fair thing. I mean, if we can't, if there's no way to distinguish it, it's not a great theory.
So is string theory not a theory then?
Well, let's not go there.
Okay.
I knew, we will descend. I'm happy to take your questions and have a discussion. But at the same time, we got work to do. So, all right. So with this said, we're going to get started. And the first thing that is important in E&M, and this is sort of like, you know, this is one of these religious wars that I've kind of lost, but, you know, you're stuck with me. And I'll explain. And it's the question of units. Now, there's a lot to be said about what we mean by units and how we choose them in the way that we write down our models and predictions, right? There's the notion of units, which I would say is related to standards. So, you know, there is the System International, SI units, right? And there's something called NIST. Does anyone know what NIST is or what it stands for?
National Institute of Standards and Technology?
Yeah, standards. Standards and technology. And they're under the Department of Commerce. NIST is not within any science organization, it's within the Department of Commerce because in order to do commerce and have a way in which we can have shared trade and shared stuff that works, they're compared. There are standards, and those standards are chosen somehow. They're chosen these days somehow. The system of standards is chosen so that, in some sense, anyone can decide, can figure out by doing some experiment locally where they are, what the standards are, what a meter is, what a kilogram is, et cetera, et cetera. So standards are, in some sense, related to what I would say is technology. But there's another notion of units that I think is particularly important in physics, which is scales. So when we, in mathematical terms, we often want to do approximations. We want to say, this is really negligible. This is really small compared to this. But what does it mean to be small or big? It's a relative thing, right? When we talk about scales, we're looking at things, it's all about relative relations, right? So we might think about what is this scale big compared to the size of an atom or not? And so the notion of scales is often related to what we would call natural units. So if you study atomic physics, there's something called atomic units, right? And because you want to measure things in the scale of an atom, you don't want to measure them in meters. And those natural units are usually defined by physical constants. And those physical constants might be things like h bar, right? If you're talking about quantum mechanics, that's a scale. It's what's called the scale of action. But it tells me something about a scale that's determined. If we're talking about relativity, we got the speed of light. And if we're talking about atoms, we're thinking about electrons. So there's the charge of the electron, or the mass of the electron. If we're doing nuclear physics, we might be thinking about quarks. And so these things tell us the scales and the units, okay? So ultimately, we want to think about the units that help us, in my opinion, if we're doing physics, to think about the scales and things that are related to physics. And some of the units that we use in E&M go back really to technology. And the telegram in 19th century England, we'll come back to that. Why is the ohm defined the way it is? Why is the ampere defined the way it is? Does anyone know? This drove me crazy. I'll tell you about it today, a little bit, right? There's another aspect of this, which we all know as students of physics, which is the power of dimensional analysis. If you write down an equation, the first thing you should do is, are the units right? Right? Does the left-hand side of the equation have the same units as the right-hand side? Now, does anyone know what the unit of capacitance is?
Farad.
It's a farad. Now, what the hell is a farad? And how is it? What?
Coulomb for volt, but
It's a
there's a volt for Coulomb.
right. So, but at the end of the day, what capacitance is about the shape of things. And the right unit, as we'll see for capacitance, is area. Because that's what really is determining these things. Come back to this, we'll see why.
Give us the parallel plane.
So when we want to think about capacitance units, okay, so here's another diatribe. You ready? Now, of course, when we think about the units, we all use the metric system. And there are kind of two classes of systems of units that we use in the metric system. In the System International, what we use is what are called MKS-A. MKS stands for meter, kilogram, second, ampere. Okay, so those are the standards in the SI units. There's another set of units, which is CGS, which one uses the centimeter, the gram, and the second, and that's it. And in some sense, the charge is derived from these. We'll explain that in a moment. Now, of course, we all, as scientists, we all should use the metric system when we're doing science. But if I want to measure a person, I want to measure them in natural units. And the natural unit of a person is a foot. Because I got a foot, and why should I measure me in centimeters? You know, or why should we care about when water boils for the weather? Hot is 100, and cold on Earth is 0, and the body can feel 1 degree Fahrenheit. So we shouldn't, it's good. We should use natural units. My diatribe for today, the imperial system, America first. Okay. That's all right. Yeah, joke. I strike that from the record. All right. All right, let's come back to this. So now if we come back to thinking about the question of units in E&M, then the question is, how should we define coulombs and amps? Okay? Because are they new units, or are they related to something that's going on that's a physical process? Okay. So, you know, these units of mass, of length, mass, and time are related to mechanics. Mechanical forces that gave us accelerations, Newton's laws, and it told us how to relate mass, inertia to acceleration, etc. But now we have new forces. In E&M, we have new forces. And so if we think about this, so let's start with electrostatics. So electrostatics is the situation where we have charges fixed in space in some reference frame. Okay, so the charges are not moving. So if we just think about the basic force that we all know, you have Coulomb's law. And Coulomb's law tells us if I have two charges, Q1 and Q2, at some fixed position, the notation we will use will have some origin, and there's the position relative to the origin, which we'll call x1 for that, and x2. So capital X represents the position vector. And then we have the relative position going from 1 to 2, x2 minus x1. Okay? And so Coulomb's law tells us that the force on charge 2 due to charge 1, empirically what we see is that it's proportional to the product of the two charges and inversely proportional to the magnitude of the distance between them, and in the direction, which we'll call r hat, a unit vector from 1 to 2. Now, I didn't say equals here, I said it's proportional to, okay? And the proportionality constant could be anything we want. We'll call that proportionality K1. And that proportionality constant tells us how to relate the unit of charge to the units of mechanics, because the force is mass times acceleration. So it only has mass, length, and time in it. The right-hand side of the equation has some notion of charge, which is a new entity. And we have anything we can choose anything we want for K1, and that would determine our system of units. Okay? Right. Yeah. Someone have a question? Yes.
Yeah. So in our system of units we've defined so far, we haven't defined charge, but we have Q1, Q2, which clearly have a different unit from our Q1.
That's correct. So the units, so whatever we're going to come to this, whatever we choose for K1 would tell us how to relate whatever unit of charge we are to mass, acceleration, mass, length, and time. So let's see how that will unfold in a moment. We also have well, maybe before I do that, I should say, of course, that this picture of Coulomb's law is kind of action at a distance, right? It's saying that there's a force on 2 that is arising due to a charge that is at some distance from it, right? And of course, we know that we can re-express it. It's not particularly required that we do that in electrostatics, but it's a useful physical concept that really takes flight when we start thinking about dynamics to think about fields, right? So we have the notion of the electric field created by charges. And the electric field created by charges is local. So we define the electric field such that the force on 2 due to 1 is whatever the charge 2 is times the electric field it sees at its position. Okay? That's the definition. Now, this electric field in this case is only coming from charge 1. So the field, so there's charge 1, and charge 1 creates an electric field. And the force on charge 2 is due to the electric field at its position due to charge 1. Of course, this throws under the rug, what about the fact that charge 2 creates its own field, And is there a force on itself due to its own field? That's a really hard and complicated problem. Maybe we'll discuss that more at the end of the course. It's actually not solved without quantum mechanics. Classical mechanics, it's one of the places that classical electromagnetism fails, the question itself. Yeah.
Just to make sure I understand that statement was that the question of whether or not a charge can have effects on itself from its own field is the difficult one.
Yeah.
Okay.
Yeah, that's a problem that actually is inconsistent within classical electrodynamics. It's one of those examples of the inconsistency that I explained. But, so we ignore those cell forces for the moment. And this, of course, tells us that the electric field, due to a charge, by this expression, is K1 and divided by the unit vector. This is just another, I'm writing this in a slightly, I guess I should say, at position X. Sorry, let me be consistent with my notation. This is a slightly different way that we sometimes write this. And we'll see this later. Okay. This cube is coming because I've written the unit vector as the vector divided by its magnitude, okay? But it's really just a re-expression of what we wrote on there, okay? So again, here we will see that the unit of electric field and how we define electric field will depend on this choice of this constant K1.
So you mentioned Coulomb's law being action at distance, that fields are local, but we're still dealing with an action at distance formula here, right?
No, because what this is saying is that the force at this position, X2, is dependent on what the electric field is at that position.
Okay. That bottom equation is basically just Coulomb's law, right?
It is, but it's saying it's telling us what the local electric field is. And it comes from this. Now, how it got there is a different story. Really, it's radiation. There's a local propagation that has to bring the field there. But this is just saying there is some field here, and it doesn't know where it came from. It just says, all I know is I'm sitting here at position X2. I sniff out with my little test charge, and whatever locally is, the fact that it came from something at a distance is fine if it can propagate there. All right, good. Continuing. Let's see, this class ends at, we started at 9:30, so I guess I have till 10:45. Right? Okay, good. Pace yourself. All right, let's go. We have magnetostatics. Now, magnetostatics is a little bit different than electrostatics in that we have moving charges, okay? But what we have is current, which is charge per unit time, which is constant. So the flow of current is constant. There's no current that's converging or diverging anywhere, okay? And so the empirical law of magnetostatics is the Biot-Savart law, which says if I have, say, two currents, say, let's move them. There's a current in this wire, I'll call I1, a current in that wire, I'll call I2. There's a little chunk of this current, a differential chunk. So there's an I times a DL1, where DL1 is the length element along the direction of flow. And there's another element of this guy, DL2. So that's here and here. And again, there is some vector that goes from 1 to 2. And I want to know what is the force on this current due to this other current. That's the Biot-Savart law. Again, an empirical law. Now, magnetic fields are annoying because everything's a cross product. Okay? So, well, in this case, in the Biot-Savart law, the force on this current element due to that current element is proportional to the two current elements as vectors, and the distance between them cubed, but in everything being a cross product. So we go cross this, cross okay, and that is proportional with some constant.
And that I in front of DL1
Is I1 and I2. Thank you. Okay. So it's kind of like Coulomb's law, but instead of a charge, I have a current times a length, which has the units of charge times velocity, right? Because it's current times length per unit time, so it's charge times velocity. So clearly, you know, we're going to have to do something with K1 and K2 to have consistency if these are both going to be forces. In addition, we can think about this, of course, in terms of a field. So in this case, the force that this current feels is due to the magnetic field produced by this current. And in what direction is that magnetic field going? So right here, the magnetic field is out of the board, right? So the magnetic field, again, there's units here, and the magnetic field, if we say that the force here is related to hold on a second, let me just see one thing. Got my cross products right. I got this backwards. Yeah, I did. I thought so. Because that is the magnetic field due to charge 1, and this is the force on it. So it's QV cross B. Yeah, that's correct. So the field due to current 1 at position x2 is proportional to all this stuff. So we can write that as alpha. We'll have a new constant. I introduce this additional constant because I have freedom for how I choose the magnetic field units relative to the electric field units. Okay? I can make any choice I like. I should mention one other thing in terms of the empirical laws. If I think about the total force on this wire due to this wire, that force, if I did that integral over these two length elements, I would find that that force is infinite. So we always talk about the force per unit length. So the force per unit, the magnitude of the force per unit length between these two parallel wires this is a problem that we'll do again, you've done it in your undergraduates, is equal to K2, in this case, that's this force. It's I1, I2 divided by the distance between them, and then there's a factor of 2 when you do the integral. Okay? So that's the force per distance between those two wires. Yeah?
We have our unit vectors going from 2 to 1. Should this be from 1 to 2?
So this is going from 1 to 2. That's what this is defining. Yeah. 2. Yep. 2, 1. That's this vector. That goes to 2 from 1. Yeah.
The expression for the magnetic field says it's a function of x2 vector.
This is the differential, by the way. I should have said that. It's the differential magnetic field. And it is, because it's a function of where the, again, in the same way, let me write it a slightly different way. So this is just like we saw in Coulomb's law. This is the magnetic field somewhere in space. The differential unit, this is a magnetic field just due to this one little element. This one element of current produces a magnetic field, and what it is, as a function of where I'm looking, is this. The force is related to this, so in this case, what we have here, the force here depends on this times the magnetic field. Okay. Yes, I'm listening.
What is the factor of alpha standing?
So at this point, K1, K2, and alpha determine our systems of units. They allow us to relate the units of charge and current to forces and fields. And the different systems of units that are used and the religious fight that ensued for all of the 20th century had to do with what we should choose for these different constants. So now I'm going to tell you what the different choices are. Right. So there are what I'll call the arcane choices. Oh, before I do that, I should say there's one very important fact that I forgot, which is we can do these two experiments by having fixed charges, measuring what those forces are in some way with some forceometer, and do the same thing with a certain, that charge that's flowing, having chosen some choices, and that relates, the forces these have to relate, the same systems of units, they need to relate. And what we can show is that empirically, okay, so first of all, we can just look at dimensional analysis. What this tells us is that because K2, where is that? So K1 relates force to distance squared and charge squared, whereas K2 relates force to charge times velocity squared and distance, that the ratio of these two things has to be equal to a velocity squared. Is that clear? Just from dimensional analysis. Because this thing on the right, I dl, is a charge times a velocity. Okay, so that means that K1 and K2 don't have the same units. And they are equal, the units of these is a velocity squared. Guess what velocity squared it is? C. It's the only thing and so this is empirically true. And it's amazing that this can be found in statics. There is no radiation here. If I just did these experiments and I would measure these forces, I would find this fact. So this is a constraint that we have. Whatever we choose for K1, whatever we choose for K2, the ratio of them is a velocity squared, and actually what it is the speed of light squared. And the speed of light is defined to be 2.9, gosh.
3, take it or leave it.
God, do it right in here. 998 times 10 to the 8 meters per second, which is approximately 3 times 10 to the 8. But there is actual, in the system of units, the speed of light is actually fixed. Okay, it's chosen to be a particular number in our units. Okay. Very good. So, with what we've said so far, we can now define different systems of units. Let me use this word. So, there are arcane sets of units that we no longer use, but they're important to just, because they're where our modern units come from. In arcane units, first of all, we'll set alpha to be equal to 1. Okay, so we're not going to have any new constant. We just set alpha. Don't introduce anything new. Okay? And then we have what are called ESU, or electrostatic units. In electrostatic units, we're just going to choose K1 to be 1. Okay? We're not going to introduce any proportionality constant. We're just going to say that K1, and that defines charge in terms of mass, length, and time. Interesting. So there's not a new unit, although we can call, in ESU, the unit of charge is called the ESU. And one ESU is such that if I look at the force between the two charges, so this tells me that charge squared divided by length squared is equal to acceleration, which is mass times L per unit times squared. Okay, so this tells me that one ESU is equal to the square root of the unit of mass times length cubed t to the minus 2. So for example, if I chose my mass to be CGS, that would be a gram, a centimeter, and a second, right? Then this would tell me that when those things are separated by 1 centimeter, if I had one ESU of charge separated by 1 centimeter, I experience 1 dyne, which is the unit of force. It's a 1 dyne is a gram centimeter per second squared. Now, how many newtons in a dyne? You got to think about your factors there. 10 to the minus, what is it? 5. Yeah,
So if I'm just plugging in K1 is 1,
yep.
shouldn't Q squared over L squared be a force then? Or am
It
I
is.
missing something?
It is.
But you just said it was an acceleration.
Mass times acceleration.
Oh, okay, I'm sorry.
Yeah. Mass times acceleration. Yeah. It's a force. Okay, so in this case, then, of course, we have to have, because of what we said over here, that says that K2 is 1 over c squared. Okay? And that defines then, because if I have that 1 over c squared, then that cancels out the velocity up there, and I'd have charge squared, and it will all be consistent. But the unit of current would be in terms of ESUs per second. Okay? There's the other choice, which is EMU, electromagnetic units. And in this case, we do the opposite. We'll choose K2 to be 1, and we'll choose then K1 to be equal to c squared. Okay? Now, in this case, we have a new unit, which is what's called the absolute ampere, or the ab amp. Okay? So the ab amp is such that if you were to have, if I look at that equation for the ab, if I put 1 ab amp here, if I choose K2 equal to 1, then the force per unit length, which is, say, 1 dyne per centimeter, is equal to an ab amp, or in this case, 2 dynes, because it's 2 dynes per centimeter is equal to 2 times 1 ab amp squared per centimeter. Okay? So in this case, the current is defined in terms of the mechanical units. Whereas in ESU, the charge. Welcome now to 19th century England, where they were making telegraphs, and this unit of ab amp, 1 ab amp, was a huge amount of current, way too much current to be thought of as the natural unit of current. So instead they said, we need to define a new unit called the ampere. Hold on a second. So we have the ampere, so we defined the new amp there as 0.1 ab amps. That's how the amp was defined because of what was going on in telegraphs. And it was using the EMU units because they cared about currents and they cared about telegraphs and they wanted a natural unit. And the unit was, well, about 1/10 of that is about the current that we send through these wires. And so the ampere is then defined in terms of the force per unit length such that I get 2 times 10 to the minus 2 dynes per unit centimeter for 1 amp running in wires separated by 1 centimeter. And this was the actual definition of, in NIST, of the amp. The amp is how much current flows such that I get this much force per unit length, which is 2 times 10 to the minus 7 newtons per meter. So for decades, this was the definition of the amp. It's how much current should I flow if I take 2 wires and I separate them by 1 meter such that the force is equal to this. And it came from this craziness. Yes, we had two questions, yeah.
Oh, is that a square on the 2 times 1 add-in?
Yes, right, because it's current squared, yes. Yeah,
So the dyne isn't a consequence of any one of these analyses. This dyne is just a separate thing that is
Yeah.
present in both of these.
the
Yeah.
dyne is just the unit of force, which is mass times acceleration.
Okay, so
In centimeters, grams, and seconds. So you may recall, come as the definition of mu naught is going to come in here. It's related to this something times 2 to the minus 7 because that's just the way it is. It came from this. Okay, so none of these units are what we actually use now, but there's one that's very close to this, and that is two sets of units. There is what are called Gaussian CGS units. And these are the units we're going to use in this course. You're going to learn to speak ancient Sanskrit, also known as Gaussian CGS, because these are Gaussian. Let me explain why. Now, there's a problem. The problem with ESU is that in ESU units, it's nice that we don't introduce some arbitrary new constant here. We just say K1 equals 1. In which case K2 has to be equal to 1 over c squared. However, the problem, if that is the case, and we choose K2 to be 1 over c squared, and this has the units of charge times velocity, then the units of magnetic field are not the same as the units of the electric field, because the electric field is just charge over distance squared, and this would have charge over velocity over c squared. And that's dumb. The units of electric field and magnetic field should be the same, because as we know from modern physics, a magnetic field is just an electric field seen in a different reference frame. So they should have the same units. And so in order to do that, we have to choose alpha not equal to 1, but alpha equal to c. Then we have, in this case, the magnetic field, due to some current at position x1, would be I1 dL1 over c crossed into and the electric field of a charge at position 1 there is no mu naught. There is no epsilon naught. There's only C. All right? Notice that these have the same units, right? This is a charge times velocity divided by velocity is charge per length squared. The units of magnetic and electric field is charge divided by distance squared. Okay? And they're the same units. Now, these are not the Department of Commerce standards. We would never use this. We'll have to convert ultimately. But if we're doing physics, we use this. Okay? The units are different. There's the unit of charge is an ESU, which is in CGS units is what's known as a stat coulomb. Now, what the hell stat stood for, I forget. The same thing, but it's the same unit, and it's exactly what we said over here in one of our boards. Let's see, where is it? Is it here?
Oh, yeah.
This guy. So it's centimeters cubed grams second. We never make that conversion, but there is a relationship between the unit of charge, because we have no constant like epsilon naught or anything else over here. In the Gaussian CGS units, the unit of charge is related to the mechanical units of centimeters, mass, and second. Yeah.
Divided by 0 and log of your electric field.
Yeah, I did. Yeah.
So was was alpha equal to 1 not important in defining ESU then, if we're now using it when alpha is not 1?
It wasn't. It was important. It wasn't important in determining the charge. It was important in determining the magnetic field.
Okay.
Yeah.
So the ESU does not depend on alpha equal 1?
No.
Okay.
Yeah. Okay. Very good. So CGS units, if we use the CGS units, and this is of course what Gauss used, why they're called Gaussian units, we use centimeters, grams, and seconds. Okay? The speed of light, in that case, is approximately equal to 3 times 10 to the minus 10, 10 plus 10 centimeters per second. The other set of units, which is most likely, I would say for almost 100%, how you learned it, are what are called SI MKSA units. Okay? What are the choices in this case? Well, K1 is chosen to be, this is also known as rationalized, I don't know how rational is, MKS. I'll tell you what the term rational means in a moment. And K1 is chosen to be 1 over 4 pi epsilon naught. K2 is mu divided by 4 pi, mu naught. The ratio of K1 to K2 is equal to 1 over mu naught times epsilon naught, which has to be, of course, equal to c squared.
I assume that when they created the epsilon naught U naught form of these
Yeah.
units, this isn't how they did it. They didn't make K1 and K2 and say, now we're going to define.
No, that is.
It was. There
Yeah.
wasn't.
Yeah.
Because
And
4 pi pops out a lot of places.
Yeah, I mean, it was, there's another set of units that I didn't explain, which are Lorentz Heaviside, which is this, where I put the 4 pi's in. So there's another, so let's get this. Well, where the hell did 4 pi come from? The reason is the 4 pi's were put in there so that the 4 pi's didn't appear in Maxwell's equations, which we'll explain in a moment. So it was a way of, in my opinion, why would I do that? The 4 pi's tell me something about geometry. I don't want to get rid of the 4 pi's. But it was put there in order to get rid of the 4 pi's in Maxwell's equations, which will appear explicitly, as we will see in a moment. And the mu naughts and epsilon naughts came from saying, well, there was an old-fashioned theory where it said the vacuum was something made of the ether. And the ether had a permeability and a permittivity. And these were the permeability and permittivity of free space, of which it doesn't exist because there is no ether.
These are remnants of the ether?
Yeah. Yeah. That's why they are. And so in Coulomb's law now we have that the electric field then at a point is 1 over 4 pi epsilon naught times the charge, and if it's at position 1. And the magnetic field is mu naught over 4 pi times the current crossed into this thing. Okay? So I want to conclude this in the last 2 minutes with writing down Maxwell's equations in these 2 sets of units. Okay? So let's just do that. and then we'll come back. So the two sets of units we have are CGS Gaussian, and Maxwell's equations are as follows. In SI. You probably recognize these. These are less recognizable to you, but we will learn together. Notice the difference between these two sets of equations. There are 4 pi's explicitly in Maxwell's equations, and there are no 4 pi's here. The 1/4 pi's and the 4 pi's that appear in the definitions of K1 were put there to get rid of the 4 pi's in Maxwell's equations. And there is another set of units, which I said is called Lorentz-Henstein, which is Gaussian CGS, where you get rid of the 4 pi's now.
And then some people write C equals 1 in Gaussian.
They do. I mean, that's a whole other thing about if you wanted to use natural units in relativity.
In the back of Jackson's book, I don't
Yeah.
remember seeing C.
They are in edition 2, which is the one that I use.
Wait, I thought we used edition 3.
But this is the third edition. There's a couple of things I want to say about this before we conclude, okay? And then we'll pick this up next time. Notice dimensional analysis. The right-hand side and the left-hand side have the same units. How could you check? Well, let's check this. What is rho? Rho is the charge density. What are the units of charge density? Charge unit volume. Does the left-hand side have the units of charge unit volume? Easy to see, because the electric field is a charge per unit length, and the gradient, a length squared, and the gradient is 1/length. It has the same units. I don't know what this is a farad. Does this have the same right units? I wouldn't know. Maybe you would, I wouldn't. What about here? Yes, Faraday's law. C times T is a distance. That's the same thing as a gradient. E and B have the same units. I love it. Same here. Charge density, current density is charge density times velocity. The velocity has the same units as rho. So these have the same units. Okay.
Or with 2 less constants.
Okay. All right, we will pick this up. We will learn together. I just wanted to say one last thing. This is Jackson edition 3, where it used to be in Gaussian CGS units, but he got beat over the head by the Système International, and they said no. But he gets to chapter 11 in this thing. Yeah, so chapter 11, special relativity. And inside the box, he says the following. Beginning with chapter 11, we employ Gaussian units instead of SI units for electromagnetic fun. Explicit factors of C appear in a natural manner in these units, making them more appropriate than SI for relativistic phenomena. These issue of rationalization, expression of 4 pi is another matter. This is all discussed in the book. So I ask you, why was that not true in the whole book? I mean, it wasn't just true for relativity, it's true always. We're gonna learn how to use these things. All right, have a good rest of your day.